Okay, let me share my desktop first. And so today we will be looking at dynamic programming. Earlier, we had looked at it from a very basic recursion perspective. And what we were doing was we took one of our standard recursion problems. This was, I think, Fibonacci here. And we came up with the standard methodology, which is we will start with recursion initially, add memoization or some sort of cache, and then that improves, and then we add it to iterative plus cache, and that is called dynamic programming, right? So these are the steps we have been doing, like recursion, add data structure, it's called memoization, add iteration, it's called dynamic programming. Okay. And in this case, if you remember, there's also an optimization on top of DP, because in this particular case, you can always get rid of the metrics that we are using or the data structure we are using. But those are all like very smart things we don't know, almost nobody asks in the interview questions. Okay, today what I'm trying to go through is this one standard problem. It's called the gold mine problem, or you might even encounter this as like the edit distance problem. So let's see how to work this out. So I'm switching to the other sharing now. Yeah, stop sharing. Okay, this one, correct. So now I think dynamic programming, maybe dynamic programming lecture 2. Can you see my screen?
Yes.
One where I have the whiteboard?
Yes.
Lecture 2, but okay. That's fine. Okay, so let's talk about, so I'll just recap what I was telling you just a second ago, which is so the very particular way we approach dynamic programming in this class is we write everything as recursion. We start with it and we add data structure to it. What is going on? Recursion. We add some kind of a data structure. We call it memoization. So that itself is an improvement on the brute force approach. And when we add plus iteration, it becomes dynamic programming. And the reason why we are doing all this is exactly how the scientists thought of, like everything in the beginning was recursion, and then they started thinking of how can we improve, and people started coming up with interesting things like adding a cache, and adding all the like iterative thing. In fact, dynamic programming, lots of people agree it's a terrible name. It's neither dynamic, it's not programming. All you do is add a memorization and iteration in some cases. But okay, having said that, the reality is this shows up more than anything else in interview questions. So today's question is gold mine problem. There are some varieties of this. One is the knapsack problem. Okay, so knapsack. So this is a thief gold mine problem. There's a thief knapsack problem, and I'll tell you how this is different. You might even encounter this, a flavor of this in as edit distance. Okay, are you familiar with these problems?
Yes, I'm familiar with these.
Okay. So I'll anyway, I'll just, the question here is, we'll start with gold mine. Gold mine question is, here is a mine. Actually, I already have grids. I can, for the first time in my life, draw straight lines. Okay, so here's the grid. So you are a thief, right? So here's a grid, and when I say grid, it's basically layout of a gold mine. And the gold mine, the layout is, there are some pockets which has more gold than others. So let's say we'll name it in single digit numbers, 3 and okay, 2, 5, 1, 7, 6, 5, 3, 9, 7. Randomly we'll name it. And your goal, you are a thief who's standing at the beginning of the gold mine. Your goal is to get maximum gold possible by the time you get through the whole mine. You can only go through it once. whatever. So at least find a path, right? Find a path that return a path which will give you maximum gold. Okay, and so what we are doing is to remind you the standard stuff we are doing. Our very first step is paraphrasing. Okay, second one is logic, right? Okay, second one is logic. Third one is our try, run, edge cases, now checks, online code editor, which we have not been doing much, but it's important we think of the logic before we code up, read out loud if we get to that. Okay, so now here in the question, the only criteria is if you are in a one given cell, you can only either go, change the colors, go here, here, or here. Basically, you can either go straight, top, or bottom. That is the only criteria. Now, if I ask you, how will you solve this? What are your steps?
So we can probably start from the first row column and choose the maximum value as the starting point. For example, from the first column, we'll choose, okay, we will start with 9 itself. We'll not explore 4, 3. And once we have chosen 9, we will trace all the 3 possible paths that we can take from 9, which is we can either go to 2, 5, 1. So we'll call recursively on these positions to get the maximum value from those 3 options.
So you're saying you will try out 9, try out 4, and try out 3 and pick the maximum from them, is it?
No, actually, since there are no negative values, I'm only thinking that we can just start from 9 and we need not explore 4 and 3.
Fair. Okay, that's a fair argument. But then here's my counter question. So let's say the grid was differently populated, right?
Okay.
So this is always, all these lines are ones, and this is all nines. Okay. So you are saying we start from 9. The moment you start from 9, you're stuck. Either you can go here or here, your maximum is going to be about 10 or something, right? But here, if you start
Oh,
from
okay.
3, your maximum might be already by definition like 30 plus 9 3 is 27, 30 plus. So the goal is to find the maximum goal you can earn, and that might or might not start from the highest value in the first column.
Oh, then I understood the problem incorrectly. So how, like how you drew 3 arrows from that cell, right? I thought from any given cell, we can have like 3 options.
Which is right. So I'm saying any given cell, you can have 3 options, even in the case when you start at 9. So all I'm saying is you are starting out on the wrong foot, because let's say if from 9, your options are you cannot go up, there's nothing left. You have only 2 options, this one or this one. Let's say you pick this one. So now only you have 2 options here and here. Even if you pick this at this point, and let's say you go to 9 itself, right, instead of any of the other 3 options, you still don't get the biggest number, because the biggest number is achieved by having 3 9s together. Okay, so my point is, this is a very interesting question. It's a very simple question if you think about only in the recursive way, which is, if I am in the center, what options do I have? But the only mildly interesting thing here is your first step.
Okay.
Okay,
So
now how will you
in
do
this case, I think we need to explore all the 3 possible values in the first column. So we will have a for loop that will go from the first value in the first column to second, third, and with those as starting points, we will recursively call and store the maximum that we have obtained.
Okay, so what you're saying, if I understand correctly, there is a main, right? And main, there is one first one, which let's call it helper function, right? Helper function. And then there is the actual, what you call that minor function, right? Minor function. So what the helper function probably does is, let's see, this is already writing sideways. Yeah, beautiful. So you're probably defining, let's write the signature in Java for the first time. So helper function is public static. Let's say it's the one which prints values, void helper, right? So its job is to find helper, and only input it gets is let's say let's say we give you a two-dimensional array. So we'll do int blank blank, which is your name of, which is called mine. Okay. Now, second function is your public static int. This is the minor one, miner, whose input is also, so input is two things. One is your grid of the mine, and two is your coordinates I comma j, starting coordinates, right? So you can even assume that, let's say we call this grid or mine as global. Let's say this is, it's basically you get it here, you made it what, global something, global grid. So you don't need that. Let's assume in the main there is a grid which is defined. Grid is equal to new int of, let's, I don't know, 8,8, for example, right? So, and it's already filled with values. Okay. So now in that case, I will even say we don't need to pass the grid all over. So only thing we are worried about is finding the maximum path. So if we go back to our inner function, it will be I comma j, my. Okay, so this is good. So yahan say, now I want you to tell me what was your plan for step 1.
So my plan was um, for every cell in the first column. So we will have a for loop I and j that will only iterate with row being 1, 0 to n, and column value will be constant, which is 0. So for every cell in the first column, I will get the maximum value from originating from that cell. And I will maintain a max counter, which will compare the result from that cell with the maximum value and keep updating it.
Well,
So in
yeah. So basically you're saying int I is equal to, sorry, I is equal to 0. And let's say the size of the grid is m cross n. So that is m rows and n columns. So you're saying if you are given only, let's say, m comma n, oh, how very nice. N, okay, for int I is equal to 0, I less than m, I plus plus. Okay, so this is what you're saying, right? For I is the only one, the row is the only one which changes.
yeah.
Now let's call it, let's minor. So now we're calling the minor function, and the minor function gives you a int local max equal something, and if local, let's make it more cleaner. Int local max equals the something in the minor function. We haven't even given that a thought yet. We're going in there, but all we are going to do is if local max greater than global max, we'll start at 0. Global max. your global max becomes local max. Okay. Local max. Okay. So now let's think about what we want our actual function to do. So we haven't even filled up the minor function there, the calls, but even to make that, let's write the function itself. Okay, so for that, let's write in Java only to tickle our brains. So let's call it public static, what is one, an int, because it has to return maximum minor, and all we get is some I comma j. Okay, so that is your function. So what should the I and j be coming out of here?
Sorry, I was on mute. So first it will be 0, 0, then 1, 0, then 2, 0.
Yeah, so you're saying this will be I comma 0, right? The first time it comes in,
Yes, yes.
we are reusing the I, and j starts at 0, and then that will keep changing. No, sorry, 0 comma I, right? Wait, which one are we changing? The column, right? The column is the one which is, no, sorry, column is steady and row is changing. So correct, I only is changing. Okay, so we have an answer on what the input is going to be for I. All right, so let's go back to our golden grid, golden steps. And we are here, which is paraphrasing, and we're done with paraphrasing. We are at the logic step. The first step was function signature. Now there is core, actually me, my kind of logic. Then we have exit conditions. And then we have parting gift. Parting gift. Okay, so let's go back and let's also draw another mine closer somewhere here so that we don't have to keep scrolling up and down. Maybe here, right? So here is our mine grid. It has some values. I'm going to try to replicate it. Okay. Oh, 9111, 4111, 399. Very smart. All right, whatever, doesn't matter at this point, but it's just for our visualization. Okay, so this is our visualization. So, okay, so here, now we are done with the public, the function signature. So now let's talk about me, my. Let's talk about here. Let's say you're standing here, right? Somebody tells you, you know the maximum value so far. What will be your job?
Your job will be to add yourself in that maximum value.
Okay, so that is first part. So let's say your yeah, well, let's go. Okay, let's say max value so far. Okay. Oh, the one time I had to write correctly. Okay, so max value plus you, the max value so far plus you. And more importantly, what will you do after this?
I will call on my 3 possible options to get the maximum value from them.
Right. So you're saying basically we want to somehow find 3 options, child 1, child 2, child 3, and we will add t is equal to plus t when we send it. Okay, is that right?
Yes.
Remember, this is not even, this is purely pseudo code. So probably they should
Yeah.
come.
So I will add myself in the maximum of my children and return that value.
Okay, so let's see if you want to call that. So it will be grid of I comma j, the value at grid of I comma j plus t. Okay, this is what you want to return. Oh, sorry, you wanted to also add the max value so far. Okay, so let's say that's right. And let's go to the next step, which is your function signature is done, core me, my logic is done. Now we are looking at the exit condition. When will you stop going through the grid?
When you have reached the maximum column, and when your R and C are out of bounds, basically. So if R is equal to M, I equal to M, and J equal to C, greater than equal to. So we
That's
will
fine. Let's
just
start and see because I'm
return
not
0.
row and column. So if R, your row count is greater than what?
Row count is greater than equal to um, M. It's M cross N, right? So M.
So these are M rows and N columns.
Yeah, so M greater than equal to M.
What else?
And sorry, or I think if either of the condition fails, so or C is greater than equal to M.
You mean like M rows and N columns, right? N you said. I'm assuming you meant N.
Oh, sorry, I said M, but I meant N. Yeah, thank you.
Yeah. So what will you do in that case?
In that case, return 0.
And 0. Now, there is a problem with this. What you say is right. If it was a general case where we are going through all the grids, all the rows and all the columns simultaneously. But the mere fact that we did this here does something different in this code, right? So what did we do here because of which this might not be right? It's not wrong, but there is some extra data there.
Trying to think.
So you're saying we will stop when we run out of the what do you think called the grid, which is right. So either you fall off this side or you're going down and you fall off this side. But are you really going down? I'm
Yeah,
talking
I
only
mean,
about this
which
in this function, in the minor function. I understand where you come from when you said that, okay, you either walk out of the grid horizontally or vertically. Is that still valid
yeah,
given this
because we will
case?
recursively call minor, right? So when we will call minor, our R and C will get updated. So those values may get out of bound because we will keep calling minor recursively because we will
Correct.
calculate the 3 options.
And you're saying R and C both will be updated at every second, every chance, every
Yeah,
step.
yes. It will
But why
recursively
did we
call.
do this then? Then why did we do this?
This is only as a starting point because you cannot start from any other cell. You you have to, oh, maybe my understanding was wrong. I thought we have to start from the first column.
No, you can make
So,
a choice. You have to start from first column, but you can make a choice. Which choice to make is what we are trying to find here in this loop here.
oh,
Do you
okay,
want to start
okay,
at 0?
okay.
Do you want to start at 1? Do you want to start at 3? Do you want to this, whatever steps here are?
Okay, yes. So, I don't think so. We need the um. Then we need to iterate from like we have hard coded the column value to 0, right? So we need to try from every cell. So we need to have another for loop for j, and we will recursively find answer for every cell as a starting point.
Okay, but fair. But Mike, this is something I'm thinking out loud. Okay, so basically, I might be wrong. I'm not denying that. So my question is, what we are doing in this first loop here, first loop is we are starting with the value I is equal to 0, which means we are stepping into row 0. So for the rest of our life, your row is fixed.
Yes, for just
What
of it, but
happens?
that
RNC won't change. RNC might be updated internally, but all I'm saying is, in that case, you don't even need this condition, the condition of like check for the guy who is falling off vertically, because you'll never fall off vertically, which you already taken care of by this thing. Less than.
okay, no. So if what I'm where I am coming from is, let's say you are at the last cell, okay, last row, last cell. So it will come inside the minor function with values 2, 3, 2, third row, second column. Now you will add your cell or probably check for your 3 options, which in this case do not exist, right? So either you can recursively call by updating those values first. But if you're checking your out of bounds first within the minor function, then you don't need that check. For example, I will only call recursively if my R updated R and C are out of bounds. So I will not
Hold on.
have that check.
You're already opening a recursion, which should be a red flag, because you should never open up a recursion.
Yeah.
One. Two, all I'm saying is, when you are in this first row, why do you care about if this crow's person moves from to that row? The probability, the point is, at the starting point, you are almost stuck from here. So you will not go, your row is fixed because you just need to check for column.
Okay.
Okay, tell me why not.
We need to
So
explore 3
let's say
different options, right? Like,
okay, correct. So we start exploring here. So you're saying it's here or
yeah.
here. You can go here, 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 and your point was here. Well, we might just run out of row here. Is that right?
Yes. So when you're standing at 1, last row, last column, what will you do? You will, the code doesn't know, right? It is reached the end cell. It will try to explore 3 options from that part, from
Okay,
last
fair.
cell. So when it will make those 3 options, that's when we will identify, okay, you are out of bounds, you need to return back.
Okay, I think I buy your argument because I can't remember why I decided to do this. It will come back to me in a second. So let's go that again. If R is greater than or equal to M, or R greater than or equal to this, let's work it through. Hopefully it will return to me. So we are done most of the parts of our recursion. So which is so here. So we are at this part, which is we are done with the core MEMI. We are done with the exit condition. So now we have the parting gift. Okay, so the parting gift is, how do we calculate C1, C2, and C3, right? So I'm gonna again move these guys out because we know what we are returning. And we want to now go expand. Let's expand what is the definition of C1, C2, and C3, which are the 3 steps you have to take in any random step. Okay, so what will be the step? How do you define C1?
C1 is recursively call the minor function with just by first you can, let's say you can go 1 position up, so that means the same column but row, you're decrementing the row, so it will be R minus 1 and C, which means you're moving in the up direction, up cell, so cell above me. Can we
Okay,
do that?
from C,
That move, is that movement allowed? Like moving up?
you can
What are
either
the
go to
3
top,
movements allowed?
right, diagonal. Like if you are in this cell here, 1, you can go to 6, or you can go to 1, or you can go to 9. There are 3 movements. This is top left, straight,
Achha,
or
top.
bottom right.
Okay,
So
top left.
you do not go, yeah.
So that will be C plus next row R plus 1 and C plus 1 will be the top left.
Okay, so you're saying you're already moving the row plus 1, okay, and then you have to move the column. The column is also C plus
Sorry, row
1.
minus 1. So, sorry, row minus 1 and C plus
1. Fair. Okay, ठीक है. To get, let's redraw a grid again for our understandability sakes. So you're saying if your person is standing here and he wants to go to this column, he has to go a R minus 1 and C plus 1. Okay, that's correct. Okay, what next? What is C2?
C2 will be same row but next column. So R and C plus 1.
R and C plus 1. Okay, and what is the third one?
It's the next R plus 1 and C plus 1.
R plus 1 and C plus 1. Okay, so you find the max of all these three. Okay, and then what do you do with it?
I will add myself to the 3 options, max of 3. So add myself to T and return that value.
Okay, so you're saying here, you're saying myself, the definition of myself is grid is global, grid of R comma C, that's Python itself, and plus T. Is that right?
Yes.
Okay, so we return. Okay, so my question is, why earlier you were saying there was another term there called max value. Why is that not there?
So what I'm thinking is, or maybe I said something different earlier, is what I as a cell will return is the maximum you can get if you choose me as an option. So that will be maximum of what lies ahead of me plus myself. And I will return this value to whoever has called me.
Okay, and it's not your problem what they do with it.
Yeah.
Okay, yeah, you're right. That's all I wanted. Like, that's why you had initially said, come here, sit down, sit. Don't sit down, Jide. We can sit down, you walk. No, sit down, we'll go walk. Sit down, sit. Apo, sit. No, sit first. Wait, stay. Okay. So yeah, you're right. So all we have to do is done this. So we are actually done with our code, right? So code for our recursion. So instead of let's do a dry run. Let's use this grid. We'll start with here. So when we start with, let's use a different color. So let's start initially when we say this is I is equal to 0. So we come in, the R's value is fixed for us, which is 0, comma 0 when you come in, right? And you're saying if is R greater than M, what is M is equal to, in this case 4, N is equal to 3, is R greater than M? No. Is C greater than M? N? No. Or maybe we might not need the equal to, right? We just are looking for if the value gets greater than M. Do
No,
you think this
equal to also. Yeah, because length, if length is 3, the last index is 2. So if R is equal to 3, which is equal to M, then we need to return. Because it's zero-based indexing.
Yeah, but
That's
length
why.
is 3. So let's say same example. Let's say M value is 3. Your C indices should be going from 0, 1, and 2. It should never be 3, right? Because a grid of 3 is null, or to be
Yes.
specific, grid of, we are fixing the row 0, 1, grid of 0, 2, grid of 0, 0, but you never have 0, 3, right? So shouldn't your R value stop at less than 3, right? So that's why you're saying it should be greater than, okay, fair. That's why you shouldn't, wait, hold on. Your value should be always less than 3. So if it is 3, we want to return 0. Correct, you're right, you're right. Just thinking it through as we go. I'm not even claiming I'm the perfect one. This is a mutually learning process. All right, so we came here 0, 0, R0. Okay, cool. So now we do minor of R minus 1. The first one, we come here, C1. So minor of R minus 1. Okay. Okay. And this is plus 1. Okay, so let's go back into the minor. This is coming in as minus 1. This is coming in as plus 1. You see what's happening, right? So you come back here, you hit minus 2. You hit plus 2. And you keep going infinitely.
By infinitely.
So I'm saying you come here when you're in 0th row, 0, 0, you come in R comma Z, C. So your value was, you're trying to find the first child. Your first child is like, let's say you're standing here, right? You have this child, and this child, a 3 child, but this child doesn't even exist. So that the first child is what we are trying to go to by C1. Right? In C1, we already gave it minus 1 and let's say plus 1, right? Initially, when the numbers came in, it was 0 and 0. We made it minus 1 plus 1. So minus 1 goes back here, right? And then first thing it encounters is it greater than or equal to M? No, minus 1 is not greater than or equal to 3. What is M? M is 4. Plus 1 is not greater than or equal to this one. No. Goes back here to its first child, which is R minus 1 is minus 2. And this can become plus 2. Same thing, minus 3, plus 3, minus 4, plus 4. Where do you exit? Oh, you're saying it will exit when it hits the C greater than or equal to N. My question is why? Why are we even going there?
Yeah, we can check before calling this method. We can check if we are out of bounds and then only call the method.
Fair. Okay, that's what I'm saying. So we call this method only if your row greater or equal to 0. Is that right?
Yeah, we can do that. Yes.
Okay, good. So let's come in here. So let's do dry run again. So this is exactly the point of dry run. We take some values and we trace it through. You're coming in with 0, 0. And then you have the first value, which is minor of, we come here is R greater than or equal to 0. Greater than or equal to 0. No, it should actually be greater than 0, right? Because see, if it's first time it comes, it's equal to 0. It goes back here as minus 1. So shouldn't it just be greater than 0? If row alone, row. Because our goal is we are standing on the top row. All we care about is first column and below. Right? So it should be R greater than 0. Okay. So this is good. Now, second case, let's go back again. So let's say in the first case, we come in with 0. We don't even get in there for the R value. Second case is R comma C plus 1. That is you're standing here. You don't want to go to A. You want to go to B. Okay, that seems decent. So what do you check? If R value is what? Okay, let's do a dry run. Okay, so let's see, we are starting with 0, 0, right? We came here. 0, 0, we came here. Initially, we were trying to get in here. We checked if R greater than 0. No, just come here. Now 0, so you're going in with 0, comma, 0 plus 1. So your values are plus 0 plus 1, so this is plus 1. Okay, so in second minor goes inside. So this time you are going in with 0 plus 1. Okay, so your first minor goes that, and you hit is r greater than 0. R is not greater than 0. It's not going to go in there again. Okay, so it comes back here. This comes here, it goes back to -1 again. Do we care?
So then we return 0
When
because
you hit,
-1.
yeah, the same argument from above. So, okay, fair. When we hit, you're saying eventually C will add up to a fact that it will be across the board. Is that your point? You see my problem, right? Okay, so you took care of the first C1, how C1 exists. Second time, so let's come in again, dry run. We started with 0, 0. It's 0, 0, you came in and you realized that, okay, 0, 0, my row is greater than 0. So it's not, it won't go in there. So no point going there. I want my person to just stay in this row. So which is correct. Row is the same value, right? So now you go in with the same value, which is the row is 0. And the C1 is the only one you move. That's also correct. You go in here. Second time you come in with row is equal to 0 and column is equal to 1. So it comes back again, comes here is R greater than 0. It is not, it is 0. Okay. So it comes back here again.
Can you, I can't
Okay,
see
yeah, you're
what
right.
you're
You're right.
marking.
You're right. I'm sorry. Yeah, no, you're right. You're right. We think this through, and you're saying next time it will plus 2, plus 3, etc. until it hits C plus 1, which is C greater than N. So yes, we don't, this one doesn't need a check. Your same row. Okay, how about the last one? Does this guy need a check?
C3?
Yeah. Let's think it through,
Yeah.
right? We are in this stage. Earlier we were starting at 0, 0. This time we are starting at 0, 1, 2, 3, 3, comma 0, right? First column. Okay. So now you're going in with the check that so let's say you're already here, right? So what is it here? For 0, we want it's 3, 1, 3, 2. How does we want the columns to move? And okay, yeah, this is going to R plus 1, right? So if it was 3, it's almost is starting with the like what is it? 0, 1, 2, 3. Our maximum number of rows, M rows, which is 4 rows. Okay, so you're saying we go in with, when we go in with 3 value, we go to 4. And then the C plus 1 value also becomes 1. The very first time, I'm saying again, we come in with the values of row and column, which is 3, 0. And then we go back here, which becomes R plus 1, 4, 1. So we are going into 4, and we are asking, we are going in, falling off the grid already. So should we not check if your R is less than something?
Yeah. If R is less than 0.
Okay, so perfect. So we just go R is.
Yeah, I was only thinking about upper bound, but I didn't think about the lower bound.
Yeah. So it's okay. I'm saying if we will go inside there only if the R is less than your maximum value, less than or equal to what is the thing called 0, 1, 2, 3, your n total number of columns is okay. So it means less than how many rows? M rows. Okay, that's it. Then only we go inside. Do you agree?
Yes.
Okay, perfect. I mean, you don't have to agree because I'm also literally working it out with you. Okay, highly possible that I'm wrong. But my question is there anything else we need to think of?
No, but I was just wondering why can't you add a global condition? Like rather than giving unique conditions to separate calls, let it go inside the method. And we have an if condition where we check all the 4 things. if R is greater than length, C is greater than length, and R is less than 0, if C is less than 0, in any of these 4 violations, we return true, 0. So is
Fair.
that approach wrong, or is it just a different way of
It's a
doing it?
different way, that's all. And all I'm saying is don't walk
Okay,
into a
okay.
null function. If you ask minor, the grid, eventually, if you ask grid of -1, it's going to error out somewhere. I'm making you avoid that. But that's okay. These are all minor.
Okay, okay.
Add a check anywhere. That's okay.
Okay, just a different way to play it safe. Okay,
Yeah.
understood.
So
Yeah, so I
all I'm
don't,
saying is
yeah,
we are here. Like we are thinking about the edge and the null cases. We are done. And the rest 2 parts we are going to ignore now because we are still in recursion type, right? So we wrote this problem recursively. Right now, the next thing I want to do is we add a data structure to it so that we improve the. So, okay, before that, let me ask, what is the time complexity for this?
Oh, okay. For every position, there are m cross n positions. For every position, we are going 3 steps. We are having like 3 calls on the stack. What?
Almost like this, right? It's your tree is branching out for every tree has
Yeah,
3 children. So what is the
yeah, so
complexity you think of this?
I don't know.
If you remember, that's okay. It's okay. In the tree, we had one only binary tree. We had like 2 children coming out of one node, you know? So if I tell you the total number of, so what total number of nodes is n, what is the height of the tree?
Log n.
Okay, other way around, what is the complexity?
Which complexity?
What is the complexity if I was doing a depth first search? What is the complexity for a binary tree?
2 raised to the power n.
Perfect. So how is that different than here? What is it different here?
So 3 raised to the power m cross n.
Perfect. M cross n. Perfect. So anyway, this is huge, right? Clearly, it's a terrible idea to write it recursively. So we're going to add a data structure to it. We call it memoization. And we will, in fact, do both together, iteration also. But let's see. Let me ask at least this question. Plus iteration, it will equals to dp, our basic formula. But before that, let me ask the question. If I tell you you can use some kind of a data structure, what will you use for this? Where is
For
the overlapping sub problems where because of which the grid search is going to help? Because of which
Okay, yeah.
data
So
structure will help.
yeah, because there might be, so you want me to tell a scenario where there will be an overlapping subproblem?
Yes. So what is a scenario for which where using a data structure will help? And 2, what kind of data structure?
So yeah, as you mentioned, there can be overlapping subproblems, like many different calls will end up calling the same cell. So for that, we can store the result of that cell in a matrix kind of a structure. That will prevent us from calling that recursive call again and again for the same cell because we already have the result for that cell.
Perfect. So you're saying, let's say this is the cell, and first time you encountered that cell is as the down of this guy. So next time you'll encounter that as a straight of this guy and top of this guy. But why, if you actually store it in step 1, you can just retrieve it. Is that what you're saying? Perfect.
Yes.
Yeah, that is the only thought process. We can, let's get out of time probably. Let's do this both together in the next class, the memoization and the iteration. But just give it a thought. Like if this was iterative, how would you write it? And how will you use a grid?
Okay. Okay.
Like, do this as a homework, right?
Will
Do this
do.
as a homework, which is we'll
Yes.
work
Yes.
through in the answer. The homework is 1, add a data structure, 2, plus iteration. Okay, and do it step by step.
Okay.
Otherwise, your mind will get very complicated too fast, too soon. All right.
Okay, okay. We'll
So I'll
try
see
this
you
out
in
as
the next
homework.
class. Okay. Bye.
Yeah, thank you.